Hello everyone, this is batch 10 from CSC AML department. Today we'll be presenting our project on operational forecasting of regional ionospheric TEC maps 1 to 3 days in advance by convolutional LSTM and self-distillation model. This project was carried out under the guidance of Dr. K. Shivakrishna sir. This is the outline of today's presentation. The ionosphere plays a vital role in the propagation of radio and satellite signals. Its total electron content, called TEC, directly affects the accuracy of GNSS system like GPS and NavIC. During space weather disturbances, the ionosphere shows a complex nonlinear variations. Traditional models like IRI and NEQUIC fail to represent this accurately. To solve this, deep learning methods like convolutional LSTM are used to learn spatial and temporal dependencies. In this project, we develop a convolutional LSTM based model to forecast up to 3 days in advance for Hyderabad and Bangalore regions. This helps improve satellite communication and navigation reliability. Accurate forecasting of ionospheric TEC is important for reliable satellite communication. In this work, we use a convolutional LSTM based model with a self-distillation mechanism to predict TEC maps 1, 2 and 3 days in advance. We use TEC data from ISRO's Gagan system and space weather indices like KP, AP, DST and F10.7 from NOAA and NASA. The model learns spatial and temporal patterns and gives stable RMSE performance. Self-distillation improves generalization and makes the model robust under different conditions. The objectives of our project are to develop a regional TEC forecasting model for Hyderabad and Bangalore for 3 days ahead, to use a convolutional LSTM to capture spatial and temporal dependencies, to integrate self-distillation mechanism where a teacher model transfers knowledge to a student model, and to evaluate performance using RMSE across different prediction horizons. In the literature survey, we studied different research papers. Convolutional LSTM models were used for global TEC forecasting with good RMSE performance. Bi-LSTM models performed well for regional predictions. GAN-based models produced high-quality TEC maps but were computationally expensive. Hybrid models like EEMD-LSTM achieved high accuracy. However, these models have gaps such as poor performance during storm, high computation costs, lack of multi-day forecasting, limited regional focus. In existing systems, traditional models like IRI and NEQUIC are used. These models fail to capture nonlinear ionospheric behavior. Some machine learning models only handle temporal data and ignore spatial dependencies. Many deep learning models focus on global regions and perform poorly under unseen conditions. They also lack self-distillation, which reduces robustness. As a result, they show high errors and poor performance during. In our proposed system, we use a hybrid deep learning model combining convolutional LSTM with self-distillation. We use multiple data sources like TEC maps and space weather indices. The self-distillation mechanism improves generalization and reduces overfitting. The model learns both spatial and temporal patterns. This results in better prediction accuracy and improved performance during extreme conditions. We use regional TEC data from ISRO's Gagan system for Hyderabad and Bangalore. We also use space weather parameters. The data is processed into tensor format with shape 24113. We have training and validation samples for both regions. The dataset is used to train and evaluate convolutional LSTM model for forecasting. For hardware, we use systems with Intel i5 processors or Ryzen 5 processors. Minimum 8 GB RAM and SSD storage are required. For software, we use Python with libraries like NumPy, Pandas, Matplotlib and scikit-learn. We use convolutional LSTM for modeling and tools like VS Code and Jupyter Notebook for development. This slide shows the architecture of our proposed system based on convolutional LSTM model with student-teacher setup. We start with multiple input sources such as solar and geomagnetic activity, historical TEC maps, and space weather indices. These inputs represent both past ionospheric behavior and environmental conditions. Next, the data goes through a processing stage where it is normalized, converted into sequences, and combined together. This ensures the data is structured properly for the model. After that, the data passes through a knowledge refinement stage, where the model is guided using ionospheric behavior patterns to improve prediction accuracy. Then comes the core part, which is the self-distillation convolutional LSTM model. It consists of two models, a teacher model which is trained first and learns the patterns, a student model which learns from the both actual data and teacher outputs. This process is called self-distillation. We use a combined loss function that considers both actual values and teacher predictions, which helps improve accuracy and reduces overfitting. Finally, the model generates TEC map forecast along with uncertainty. There is also a feedback mechanism where new data is added back into the system, helping improve future predictions. Overall, this is the architecture that helps in accurate, stable TEC forecasting. First, we collect TEC data for Hyderabad and Bangalore from ISRO's Gagan system. The data is cleaned, normalized, and reshaped into sequences with tensor format. Next, we design the convolutional LSTM model. It includes convolutional LSTM layers to capture spatial and temporal patterns, batch normalization for stability, and dense layers for final output. We use mean squared error as the loss function and Adam optimizer for training. We then train the teacher model using dataset and evaluate it using RMSE. Then we apply self-distillation. The student model learns from both actual data and teacher's prediction. We train multiple student models with different alpha values. Alpha controls the balance between actual and teacher learning. Finally, we select the best model based on the lowest RMSE value. Then we perform iterative forecast using selected student model. Each predicted value is fed back into the input sequence to generate the next prediction. This allows us to forecast multiple days ahead. Finally, we visualize the results by plotting training and validation losses and comparing actual and predicted TEC values. We also generate RMSE comparisons for different time horizons. This slide displays the main block of code where convolutional LSTM model is implemented. This graph shows model training loss and time series forecasting graph comparing past data and future predicted values. This image displays training logs showing improvement in RMSE from trained and untrained student model. This table shows RMSE and MAE values performance of the convolutional LSTM model on different days. These are the graphs comparing actual teacher and student model predictions for one day forecast. This image shows error distribution plots showing how prediction errors are spread for teacher and student models. In conclusion, the convolutional LSTM model successfully forecasts TEC maps. Self-distillation improves stability and generalization. This model provides accurate multi-day forecast under different conditions. This supports GNSS and space weather applications. In future, we plan to extend this model to more regions. We will integrate real-time data and improve visualization. We also plan to explore advanced self-distillation methods. We have worked on patent based on our project. The patent has been successfully accepted, which validates the novelty of our work. Next, we have prepared a research paper based on this work for an IEEE conference. The paper has also been accepted in the IEEE conference, showing the research contribution of our project. Now coming to the references, these are the sources we used for our project. We sincerely thank Dr. K. Shivakrishna sir and the Department of CSE AIML for their guidance and support. Thank you. This is our project's UI. Here we can select two cities, that is Hyderabad or Bangalore. we can see that the current predicted TEC value is up to 2.92 and the day 1 forecast points up to 3.57. The anchored value is 2.92 and the data is fetched up to 24 hours, 48 hours and 72 hours in advance. The spatiotemporal track predicts 72 hours data using 120 hours history of the past data. Here we can see day 1, day 2 and day 3 of predictions. Similarly, we can see the Bangalore data also. The Bangalore's anchor TEC value is up to 3.05 and the fetched TEC values are accordingly presented.